Exactly. How do you make that when you're out? Because we have these.
Let's begin. We're going to talk about the exponential
Logarithm. Oh, yeah. It's a long story. It's because I'm taking my character. It's like in advance, so
what's the
I
logarithm?
want to take it because I'm changing my
A log of roots. Logs don't always have bases of 10. Okay, so let's talk about what a logarithm is. Logarithm of a number to a given base, they can have varying bases, we'll talk about that, is, a logarithm is just a fancy name for an exponent actually. The power to which the base must be raised to give the number. So it's actually just another way of thinking of an exponential equation. In fact, I can write this definition in as a rule. Let's do it over here. So we'll call rule 1 of logarithms, the definition and notation. So here it is. The logarithm of a number, call that number b, to a given base, a. Right, so you write the a is a very small number down here, b is something like this. The log you can actually think of as a function, we'll talk about that in a little bit. So you take b and you plug it into the log. The logarithm of a number to a given base is some other number, which is the power that you need to raise the base to in order to get the number. So basically when you write that, what it means is, if I take a raised to this a raised to the c, I get b. They mean the same thing, right? So I can write this equation, which is an exponential, an equation with an exponential, or I can write that equation. These two equations, they say the same thing. Basically, when you want to solve for the power in an equation, you can use a logarithm. The logarithm really makes the power the subject of the formula. So, for example, log to the base 2 of 8 is 3. Why? Because you have to take 2 to the power 3 in order to get 8. Right? That's how logarithms work. So, we want to talk about the exponential equation in a different form where the power is going to be the subject of the formula. So someone writing 2 to the third power equals 8, it's equivalent to them writing down log to the base 2 of 8 is 3. Okay? I have to raise the base 2 to the power 3 to get 8. Now, at this point there's usually an understandable reaction. Well, we already know how to say that. Why do we have to have a more complicated way to say the same thing? And as it turns out, logarithms don't make your life more complicated. They actually make your life a lot easier once you get to know them. Here's one way in which logs make it easier. We will call this rule 2. It turns out logs turn powers into multiples. If I have log to the base a of something raised to a power, I can actually take that power and move it down and multiply the logarithm. Because if you take something and you raise to a power, you multiply the powers, right? So I can go from a situation where there's an exponential relationship to where there's a multiplication relationship, and that makes your life a lot easier. So if I had log to the base 2 of x cubed, I can just think of that as 3 log of x's, right? Which I can think of as log x plus log x plus log x. Instead of thinking about something to a cubed power, I can think about adding something 3 times. That makes it a lot easier. Here's another rule. So these are the rules that I'm telling you, the rules and definitions, very important. Talk about the strategy later. Looking at you, Dan. Okay. Here's another way in which logs. Yes, you had a question?
Yeah. What's the name for the term for when you take the n? Is that, it's not expanding it, is it?
When I actually do this,
Yeah.
I don't think there's a name for it.
I don't know if there was, but I could be wrong.
I'm not sure what you're referring to. So let's just continue. Another way in which logs make your life easier, they can turn products into sums. So if I have a log of a multiplication, this is just a sum of the logarithms. They turn divisions into subtractions. So if I have a log of a division, I can turn this into a subtraction of logs in this way. And that kind of tells you if you multiply things of the same base, being base A, you add the powers, right? Divide things of the same base, being base A, you subtract the powers, right? So I can talk about the exponential rules in another form. And you're really going to see why this form is it makes your life so much easier in Calc 1 and Calc 2, but hopefully we'll see a little bit of the applications here. Here's another rule that we'll use to help us out sometimes, Rule 5. It's called the change of base formula. I'll mention a little bit later when we would actually want to use this formula. But it says you have log to the base A of B. So here's a logarithm expressed in base A. It turns out you can change the base if you want via this formula. Log to the base C of B over log to the base C of A. So if I have a base A, not very convenient to work with, I can change it to another base, namely C, and this formula will take effect, where C is a conveniently chosen base. We'll talk about the most convenient base pretty soon, well, at least in the math context. So let's see an example of that at play. Log to base 4 of 8, what's that? No, because 4 raised to the 2 is 16. So here, you know that 4 to the 1 is 4, which is smaller than 8. 4 to the 2 is 16, which is larger than 8. So it means that the answer should be somewhere between 1 and 2. But is it exactly in between 1 and 2? Is it halfway there? What is it exactly? It turns out that it's this, you probably can get it if you think about it for a little bit, but it's already kind of a challenging thing to figure out. Because 4 is not a convenient base if I'm looking at 8. What is a convenient base? 2. Because I know how to talk about 4 in terms of base 2. I also know how to talk about 8 in terms of base 2. So if I can't figure that out, what I can do is I can change the base. I can say log to the base 4 of 8 is going to be the same as log to the base 2 of 8 divided by log to the base 2 of 4. I can put in a convenient base whenever the base I'm currently in isn't working for me. And so log to the base 2 of 8? 3. Log to the base 2 of 4? 2. 1.5 is the answer. And you can actually check this. 4 to the 3 halves is going to be what? No, it should be, right? if you check this. 4 to the 3 over 2, well that's just the same as square root of 4 cubed. Well that's just the same as 2 cubed. That is 8. That actually works. That's the answer. Change of base formula. So every now and then you're working with a logarithm, it's in some base, you don't like the base, you can actually change it via the change of base formula. Yes?
So the conveniently chosen base would essentially be a factor of both numbers, B and A?
Not always.
Okay.
If your entire world is pre-calc, then yes.
Okay.
But once you go to calculus and beyond, there are bases that are more convenient, regardless of what you can factor into things as. We'll get to that very soon. So that is called the change of base formula, very important formula. Here is what I would say the above formulas. They're actually not that hard to prove, but I don't want to spend the time to prove them. Like, you must know these formulas. Must be memorized. Memorized. The following is highly recommended to be memorized. But technically, every rule that I'm about to write down, you can actually figure them out from the rules I just gave you without too much trouble. But they show up so often, it's just nice to just know them right off the bat. So, for example, where are we? Rule 6. Log to the base a of 1, the number 1 specifically. What is that? 0. Log of 1 is 0. It's always going to be 0, regardless of the base. Why? You take the base, raise to the power of 0, you get 1. It of course goes without saying that the base 0 is an illegal base for a logarithm, and it's not very convenient because base 0, everything will be 0. But yeah, once your base, the base of the logarithm is usually considered to be a positive number, usually a positive number larger than 1. Yeah, log to any base of 1 is 0. So whenever you see log of 1, regardless of the base, you can replace that expression with 0. Rule 7, I don't know, kind of an anti-rule, maybe. What is log of 0? A raised to the 1 is A. It's not 0. Well, it can't be 0. A raised to 0 is 1. Think in a specific base. Log to the base 2 of 0. How would you figure that out? What number do you have to raise 2 to in order to make it 0? Let's think of a number. Come on. Think. There's a reason you can't think of anything, because there is no such number. This is undefined. Now that should be a painful reminder to you, to know that log of 0 is undefined. Whenever you're doing calculations and you end up with log of 0 at some point, either you made a mistake, or the problem you're trying to solve has no solution. Log of 0 undefined, can't be done, right? If I have a base 2, there's no power that I can raise that to in order to make it 0, right? Because if you raise to a positive power, you get something positive. If you raise it to a negative power, you just get 1 over 2 to that power, which is still going to be positive. It will never actually hit 0. 2 to the 0 itself is going to be 1. You cannot actually do this. Log of 0 is undefined. That's going to help us deal with the domain of a logarithm pretty soon. It's also worth mentioning that the log of a negative is undefined. Right? Because our base is always positive. If you have a positive number, you raise it to a power, it will always stay positive. You will never be able to get a negative. So it turns out that the logarithm, if you start to think of it as a function, the thing you can plug in here has to be strictly greater than 0. And that's just something that's nice to know. Now, we figured this out by me thinking of the definition of a logarithm. What does it mean when I write this down? Oh, it means that power gives me this number. And you can kind of figure out these two rules would automatically fall into place. But it's kind of just nice for you to just know it automatically. Log of 1 is 0. Log of 0 undefined. Here's one that's useful. It's also painfully obvious. Hopefully, if you're thinking of the definition, log to the base a of a to the x. So the question is, what power do I have to raise a to in order to get a to the x? X, right? Totally obvious when you think of the definition. Something you should just know automatically though. If the base of the logarithm, if you plug in an exponential that has the same base as the logarithm, the log and the exponential, they kind of cancel each other out, and you just get the power. You just get x. The same is true in the reverse way, although this one is not as obvious. You will have to do a little bit of work to actually see that this is true. But if I were to do it the other way around, a raised to log to the base a of x, it turns out that that is also x. So if I take a logarithm that has base a and I plug it into an exponential with base a, it just gives me the x, the thing that was inside the logarithm. Rule 10. Not so much a rule, kind of a notational thing. What if I chose the base to be e? How do you write that expression? Ln. This is something called the natural log. So whenever you're reading anything and you see ln of x, you're talking about a logarithm, but the base is e. If you see log of x and no base is written, what does that mean? Well, it can mean a bunch of things. Very usually, most people would say this is base 10. I told you guys about Wolfram Alpha. You're typing something into Wolfram Alpha, and Wolfram Alpha says log x is a part of the answer. You know what Wolfram Alpha thinks the base is? It actually thinks of it as e. When it comes to math, e is the most convenient base. Remember I told you that e to the x is the most important function in all mathematics, blah, blah, blah. It's such an important function. Yeah, turns out for calculus and mathematics in general, everyone works in base e. No one thinks of base 10. Base 10 is more like an engineering thing and applications, because everyone count with 10 fingers. So base 10. If you are a computer scientist, so this is for like math people. Computer scientists, they like thinking in base 2 because of binary. It's all ones and zeros. They work in base 2. They live in base 2. Log x just means the standard logarithm. So it really depends on the context in which you're in. So there are just some contexts where one base is just more convenient than any other base to use, so we just decide to neglect writing the base and everyone's going to know what I'm talking about. So this is the very common interpretation, but once you start going high enough in any field, it starts to specialize itself. So log x for math people, it means base e. Why would you work in any other base? Computer scientists will work in base 2, engineers and a lot of other people. Engineers, I don't even want to say finance. Base E is also important for finance. Engineers, normal people. I don't know what to say here. Who will work in 10, and then you have to specialize people, the math people, the computer science people. It's also worth mentioning, even in math at a lower level, so if you're reading an algebra textbook or a calculus textbook, you see log x, it means base 10. Any advanced level math book, you see log x, it means base e, right? So once they know that, okay, you're a math person now. You don't have to read the book that everyone does when they're a college freshman, don't even want to know what they're doing with their lives. Now you're serious, base e is the only thing we're going to work with. So for you, and in pre-calc, pre-calc people, if you don't see a base, it means base 10. But it's more general that it's a standard logarithm. Now let's talk about the natural log for a moment. Okay, so now one thing I want you to appreciate, it's just a regular logarithm. I mean, it's a special one, it's a convenient one, but it's just a regular logarithm. Don't let the fact that there is a new notation for it trip you up. A lot of times people just get scared of a notation. Oh my god, there's a radical. We have to square stuff, right? No, don't freak out. It's just a radical. In the same way, ln x, it's just a logarithm, meaning it obeys all the log rules. So don't think that somehow it's special in that regard. It obeys all log rules. Right? So if I have ln of x to the n, I can still move the power down and multiply. If I have ln of xy, I can still split it up as a sum of logs. If I have the definition, ln of x, if I say that's equal to y, it's the same as saying e raised to the y equals x, right? Because the base here is e, we just didn't write it. So saying ln of x equals y is exactly the same thing as saying e to the y gives me x. Take the base e raised to the power y, I would get x, right? So all the rules work the same. But it's just very convenient because the calculations actually work out nicer when you're in advanced mathematics with ln than it does with other logarithms. And for that reason, if we're using some other base, and chances are you're going to be getting formulas in like calculus and higher, where if it involves logarithm and they give you a formula that describes it, they derived it using base e, but they're probably not going to tell you that they did that. They'll just tell you, oh, this is the rule. But everything they bring it back to base e to figure things out. So if you're in a calculus situation and you're in log to the base 5, what you would do, change a base formula, change it to ln, figure out what the answer is, and then change it back to base 5 if you want to. But ln, most important logarithm for us, most important logarithm. Things just work out nicer with that guy. And in future classes, you might start to appreciate why that is. But for now, I'll just say that and we'll move on. But it's a normal logarithm in the sense of the rules that it obeys. Let's talk about the graphs of logarithms. Or pre-graph, because we can use this to figure out the graph. No. Look back at rules 8 and 9. It turns out that those two rules together, they actually make a very important statement. Consider the exponential function a to the x, and consider the logarithmic function log to the base a of x. What's their relationship? Based on rules 8 and 9. What can you surmise from that relation? What rules 8 and 9 tell you? They're not equal to each other. Huh?
Don't you just switch the base and the
Well, you said the right buzzword, but what you explained around it doesn't really make sense. The rules were, if I take an exponential and I plug into a log, the output is x. If I take
Inverses.
their inverses. They're inverses of each other. Notice that when I plugged one into the other, the result was the original input. It's like I took x, I plugged it into an exponential function, I took that and plugged into a logarithm, and the log just gave back the original input. Also, if I took x, plugged it into a log function, and then took that result, plugged it into an exponential function, the result is the original input. They're inverses of each other. They undo each other. Now that has a lot of implications. This means, and here is a strategy for Kevin, since he's very interested in that. As a general strategy, we can use logs to eliminate, kill, destroy, remove powers, and use exponentials to remove logs. They're inverses of each other. The same way you kind of know if I'm solving an equation and there's something added and I don't want it there, I can use subtraction to undo the addition, right? If there's a multiplication I don't want, I can use a division to remove the multiplication. Now the question is, what if there's a power that I don't want? There's an exponential that I don't want. I can use a logarithm to remove that exponential, right? So if an exponential is inconvenient for me for a power to be there, use a logarithm, get rid of the power. If there's a logarithm and I don't want the logarithm to be there, use an exponential, get rid of the logarithm. You can use them to cancel each other out. They're inverses of each other. This also tells us about the graph of a logarithm. So you remember that the graph of an exponential, say a to the x, let's assume your a is greater than 1, we know what that looks like. Looks like this, I recall. What do you think that means for the graph of a logarithm? How would I actually find it? Yeah, but what's this strategy for doing it on if I have one picture, how do I get to the inverse of the picture? Assuming it exists. We reflect. So you look in the line y equals x, and you take the mirror image. So the logarithm graph is going to be that. Now the graph tells us something that we already figured out earlier. Notice that it never hits x equals 0. It gets closer and closer to x equals 0, but never makes it there. It also never ventures over to the negative side, because it's literally impossible for you to take a power and create a negative number when it wasn't there before. It's also impossible for you to take a positive number and with a power make it 0. It's not going to happen. So the logarithm avoids anything where x is 0 or less. So that also can tell us about the domain of this graph, the domain of the logarithm. It's all guys strictly greater than 0. Meaning you can only plug in positive things inside a logarithm. So that's the main graph here. So y equals log to the base a of x, where for the same reason like with exponential, we only care about being greater than 1, because being equal to 1 doesn't really make any sense, because you're just going to, if the base is 1, the answer is always going to be 1. Equal to 0, the base is 0, answer is always going to be 0. So we only care about greater than 0, and once we figure out what's happening for bigger than 1, taking a negative power can help us figure out between 0 and 1. So we all normally just think of things in terms of a being larger than 1. And the graph is going to look like this. So that's just a new graph that we know now. This is the graph of a log function. And as always, it's just a regular graph. It responds to transformations just like any other graph. It's a new function, but don't make it like a boogeyman or something scary. It behaves exactly the way your math rules behaved before. They behave the same way now. So if I were to take the negative of log to the base a of x, that's just me flipping it upside down. It would just look like that. If I were to say replace all the x's with negatives in front of them, it'll just flip it in the vertical axis, right? Because I can't have a negative inside a logarithm, so if I put a minus x, the x itself must be negative. It'll flip to the negative side, right? And if I have minus log of minus x, then it'll just flip this one upside down. It'll look like that, right? It'll respond to transformations. If I add a number to it, it shifts everything up. If I add a number to the x, it will shift everything to the left, etc. All the transformation rules, they're the same. It will function the same. So that's also true. So you realize that the logarithm is actually just another way to express an exponential, and it turns out that it is the inverse of the exponential. Other consequences. Last time I described to you how a exponential is eventually bigger than a polynomial, right? Like so much larger that the polynomial might not even try. How does logs fit into that picture? This picture is going to be a little bit. So let's look at logs versus polynomials versus exponentials. Especially as x goes on to infinity, when your x is getting large. How do these functions relate to each other? So remember, like x here is huge, big number. A gazillion, bajillion, trillion, bajillion. Okay, so here, if you compare something like x squared, y equals x squared, versus like y equals 2 to the x, versus like y equals log to the base 2 of x. Everyone's kind of in the same base. Your exponential is going to be the guy that's growing really, really fast. Right? So that's the exponential. Your polynomial, your x squared, relatively speaking, is going to be pretty slow. So it's gonna of course be this way. Right? Eventually, this guy's just the space between these guys. It's a lot of space. A lot of space. Right? So it gets to the point, it gets so ridiculous that eventually this guy's like 0 compared to that guy. He might as well not even be trying. The logarithm is actually the loser here. He is eventually going to grow very slower. Logs are going to be stuck way down here. So this would be like your log. And this will be like your polynomial. And this will be like your exponential. And between here, there is a lot of space. Compared to the polynomial, the log might as well not even try. He's going to be like 0 when you're relating to this guy. And then this guy's like, he's nothing compared to that guy. So you have like orders of magnitude of how much these functions outgrow each other. So this guy might as well be 0. For large x compared to that guy. And then this guy might as well be 0. Compared to eventually, you know, when x gets really large, compared to that guy. Right? So that's one of the ideas that's going to be very important moving on into calculus, especially. Exponentials, they go really fast, they're really, really fast. Polynomials, they're okay, they're alright. They're growing, they're kind of fast. Logarithms, really slow. Right? Logarithms grow very, very slow. Polynomials grow faster than logarithms, but not as fast as exponentials. Eventually, when x starts to get large, the chasm between these guys just blow up. You just have one function being so much bigger than another function that the other guy just might not exist. Kind of reminds me of that. I don't remember. Is it a religion or I don't remember what it is. But there's I'm sure it's from like a religion. I don't know. But there's like, oh, you know, what is the earth on? Oh, it's on the back of a big elephant. Oh, what's that elephant on? The back of a bigger elephant. What's that elephant on? It's on the back of a bigger elephant. Yeah, eventually math starts getting like that where it gets crazy. You know what? Polynomials, they're amazing. They're the biggest thing around. No, exponentials, there's a bigger thing. Oh, exponentials are now the biggest thing. Nope. There's a bigger thing. You're gonna go to Calc 2 and you're gonna learn about functions that they make exponentials look like they're nothing. Right? So this is the log, you know, sleeps like a log. He's pretty much on a beach, lounge chair. Polynomial is kind of like your everyday working man, goes to work every day 9 to 5. Yeah, this guy's like that guy with like 2 cups of coffee and a Bluetooth, always talking to this guy in Dubai, trying to get business deals. They're moving fast, but eventually you're going to learn about functions where, yeah, they make these guys look like they're not even trying, right? You're going to learn about things like the factorial function, exclamation, in fact, pay attention to me, right? X, right? You're going to learn like functions like this, exponential functions where the base can now change. And those are bigger than these guys. These guys might as well not even try. These guys are bigger than those guys. Those guys might as well not even try. Those guys are bigger than, and it goes on and on. You can keep going bigger and bigger and getting crazier and crazier. In pre-calc though, this is the highest we're going to get. This is the biggest, baddest function we're going to have to worry about. The exponential function. But that's how they kind of relate to each other. It's a very important idea. Logs grow slower than polynomials, which grow slower than exponentials, whenever the base is larger than 1. And that kind of makes sense. I mean, if this guy is the inverse of that guy, then his speed has to be compensated for his slowness, right? So if this guy is super fast and I want to reverse the motion of growing super fast, I'm going to have to grow super slow. So it kind of makes sense once you realize, oh, this is the inverse of that, so that makes sense. If this is faster than a polynomial, its inverse has to be slower. So that's another thing. Now, for us, it's also going to be important to actually know how to do calculations with these guys. So let's actually get through some examples here. So I just kind of told you the need to know. Let's actually put some of these things into practice. One. Let's start by just getting used to them by simplifying. E log to base 3 of 100 minus 3 18 log to base 3. Log to the base 2 of x, log to the base 2 of x squared, or log to the base 2 x cubed. Ln of the radical of x squared minus 1 over x times x plus 1. This is our first example. What I want us to do for f is I want us to combine these into one big logarithm. And I want to do the opposite here, expand this into a lot of little smaller logarithms. Each of those have their uses. So let's look at how to actually do calculations here, simplification stuff. Then we're going to look at how to solve equations. And then probably, well, this will spill over into next time, of course, but learn how to draw graphs where they're being transformed and shifted and all over the place. Simplify. this 5 here, I can bring up, right? Why? Because rule 2. So this is just e to the ln of 3 to the 5. This is rule 2. And then, yeah, if I take e and ln, remember ln has base e, so they can cancel each other, and I just have 3 to the 5th. And that was by rule, I forgot, was that 8 or 9? That's 8, I think. Yep, so that's just 3 to the 5th. Common errors. Happens all the time, don't let it happen to you. Someone saw e to the 5 ln 3. They're all excited about the fact that e's and ln's will cancel each other. So they decide to do it prematurely. And then write this as 5 times 3. This is incorrect. Why? Because you have to remember the rule exactly. Notice that in the rule, why is this one? Well, in the rule it says a to the log to the base a of x equals x. I want you to appreciate that there's nothing in front of the log in this rule. Okay. Here you have something in front of the log. You cannot apply the rule because it's not in the right form. So all those rules that I told you earlier, those 10 rules, you have to know them exactly. Once you want to apply one of them, you have to be in exactly the same position. And it's more that you just know it as a positional, spatial awareness of, was there an object here in the rule? No, you need to get rid of the object before you apply the rule. There are multiple ways that you could have done this, by the way. So another option would be something like the following. If I have e to the 3 ln of 5, notice that that is like 3 times ln of 5. I can actually use an exponential rule and write it like that, because I know that powers multiply in this situation. And then, it was 3 here and 5 here. On the inside, this would cancel to 3, and then I'd get through to the 5th in that same way, right? Here's where I use laws of exponents to help me out. And here I just use laws of logarithms. I don't care what laws you use as long as you use the right ones at the right time in the right way. So the formulas, they're your templates. They literally tell you the things that you're allowed to do. And the moment there is something that messes up your template, you can't do it. You have to do something else first. So that's something that I want you to appreciate when going through this. So we had a couple options of how to do that one here. More than one ways to skin a cat, but there are definitely wrong ways to skin the cat, so don't skin the cat a wrong way. Why are we skinning cats? Such a barbaric practice. What about B? What's that? What? Which one? Yeah? What did you do with that? Here? Okay. Then? Becomes 1. That's just 4 to the 7. Or, anyone can see another way to do this? I mean, if you were to put parentheses, it'll probably show up here. You could put another one here, I guess, but not really. Yeah?
Isn't that like the exponent equals rule 8? So
Yeah, this is like the base here is 4, the log there is 4. You can actually just cancel these right away and get a 4 to the 7. right? You can use a different rule, just make sure you're using the right rule and it's valid. So you could have done that. You could have also seen, so here's where you get to express your creativity. Not really. So there are tons of things that you could have seen first. You could have also canceled this one, right? That would still be valid. You would end up with 4 to the 7th also. Right? Tons of ways you can do it. You don't want to do the wrong thing the wrong way. So if you were to move this down here and then decide to cancel that and get a 7, that would be wrong because that's not legal. Tons of ways you can do this. Let's look at C. Whichever way you see is fine. Just make sure whatever you have, you have a reason for doing it. There's a specific rule that you're thinking about applying in a very specific way. What does that simplify to? Okay, how would you do it? Separate how?
Like two things. They have the same base.
Okay.
So E minus E5 and then the second section is 5 and 6.
Nope, this is incorrect.
Sorry.
Don't say you're sorry. Don't be sorry. Why is it incorrect?
Because we're in a division.
It would be division. See, now you start thinking about it because we know the rule. That is this, right? You can't forget the rules. There's a subtraction to the power means division in the base. So it's not a subtract. It's that, right? Don't forget any of the previous rules, right? So, okay, that would be the first step. Now what? Cancel what? Where? ln and e are right beside each other, right? So that will give me an x squared in the top. What about the bottom? Right, put the 5 up here, and then the e and the ln would cancel, and you'd have y to the 5th. So that actually simplifies to x squared over y to the 5th. Maybe I'll take an extra step and do that. So this will be equal to e to the ln of x squared over e to the ln of y to the 5th. I apply the rule that says I can take a product and move it up to the top. And then now it's in the perfect form for the rules to apply, and that's x squared over y to the 5th. There were other options here. Moral of the story, don't forget the rules. Every time I give you a rule, it'll always be valid all the time. Just because you're in a different context, don't think that the rules suddenly change. Exponentials and logarithms, they're functions like any other function. They have to obey all the same rules. So they can't break the laws of exponents. The laws of exponents is a thing, it's established. They can't break any other rules that we've set up before now. Another way you could have done it. You want to see another way if something else jumped out? Yeah?
Could you just simplify the top where the ln?
Right, so stay in the power for a while.
Yeah.
Oh, that's another rule, right? If our subtraction of logs really means a division. That's by rule 3. And now
Rule 3.
that's also valid. Right? So there are tons of different ways you can see to do this. You can kind of live in the world of logarithms or live in the world of exponentials. Because they're really the same thing, really. It's two sides of the same coin. So that gives you multiple ways to get to a destination, but just make sure you're doing a valid thing at the end of the day. You can't break another rule in your efforts to simplify more.
Could you, okay, this is going to seem stupid, but can you factor out an ln?
No.
No.
Yeah, so maybe I should actually write that as a warning. Because that's also a very common thing. And for a moment I forgot to mention it, so it's good that you asked that. You say but don't make up your own rules. Chances are. You'd be incorrect. And that's kind of a general principle. Here's the thing. Rules are very context specific. Okay? So, a lot of times people would see something like log of x plus y, and they feel like they should be able to do this, right? Because they're thinking of another rule, namely the distributive law, which is a thing, where they just think, oh, I should be able to distribute anything. But that is not true. It depends on the context, right? Here, when you see ln of this, it doesn't mean this is a thing on its own multiplying those things, right? No, it's these guys are plugged inside of the ln. It's a function. You want to think of this like an f of x. It doesn't mean f times the x, right? So logarithms cannot be distributed like a sum. That's not a rule. It's also, if you see ln of x minus y, it's not ln of x minus ln of y. We know what this is. This is when you have log of a division, right? So the other rules that you might think should work because you've seen them work in other contexts, be very careful. Chances are it's not going to work if you try to do it. Logs do not distribute across sums. They don't distribute across products. They don't. The rules that apply to them are the 10 that I gave you. You don't need to know any other rules about logs other than the ones that I gave you. And if you try to apply another rule, chances are it's going to be wrong. So just don't do it. You're only allowed to do the 10 things that I mentioned before, because if you kind of use what you feel should work, it's pretty much never going to work. So that's a fair warning. So there's a reason why I didn't tell you logs distribute across sums. That's because they don't. It's actually not true. That's an untrue statement. Logs break up products into sums. They break up divisions into subtractions. They do not distribute across sums or subtractions. So that's very important that you know that. So only the 10 rules apply. And trust me, they'll take you far. Like if you just know those 10 rules, it'll take you through calc 1, 2, 3. Like you'll never need to know anything about logarithms, about their basic functions and algebraic properties than what I told you. When you get to complex analysis, you have to take a different picture. But until then, the 10 rules is all you need to know. Don't make up any other rules or, I feel like this should be able to work. No, chances are it's going to be wrong.
See you later, Paul. George, see you later, bro. Go look in the pool. Don't hustle.
Okay, yeah.
The way I like just like bring the exponent.
You like to bring the exponent down,
Yeah.
and then this will just cancel?
Yeah, that makes a lot of sense.
Yeah.
So that would be 1.
So you'll end up with that?
And then we're also assuming that the outside is log base 10.
Yes.
So it would just be, sorry.
That's just a really fancy way of writing 4. Yes?
Was the 10 supposed to be your base? Did you just make it big? Or is it?
No.
It's not.
So the base is not written.
Okay.
So this is one of those things where the base wasn't given to you. Yeah. So it's there. You're just supposed to assume there's a 10 there because we're in precast.
You skipped D.
Huh?
You skipped D.
I skipped D. I did. I was so focused on getting this warning out there. The people have to know.
Wait, what'd you get that sign? You just like one spot on both sides.
Where?
That sign. What'd you get?
The green 10s?
Yeah.
Oh, there, it's just assumed. So if you just see log of x and no one says what the base is,
Alright.
you just assume it's log 10.
Oh.
It's just assumed. It's just an implicit assumption.
Okay.
If you see ln x, you assume it's base e.
Okay. Alright.
In all other contexts, they'll specifically tell you what the base is. Okay, what do we do here? Huh? Division? Does that help?
Is it a complex?
Huh? You can do what?
Is it a complex?
Oh, you want to do another division?
Oh no, I'm asking.
Oh, no, tell me what you think, and I'll tell you what you think.
Oh, wait. Yeah, divide it again.
Divide it again? Yeah, because that's just log of one number minus log of another number, and they have the same base, so I can divide again. Now, of course, if I divide by 50, it will be down here, right? Yes, 100 divided by 18 divided by 50. It's that. Keep changing. Now what? Now we can start to simplify. So this is log to the base 3 of 1 over 9. What's that?
Oh.
It's negative 2. Because 1 over 9 is 3 to the minus 2 power. Tons of ways you could also see that. You could go with write this as 1 over 3 squared. Then you can realize that that's 3 to the minus 2 and get minus 2, but you could be like, I'm going to split these guys now. Log of 1? 0. Log of 1 is always 0. These cancel, and I get the minus 2 that way. Tons of ways to get through. F. Let's combine them. Well, a couple ways I could do this. Division. And because that's being, I can move this 4 up. And then do a multiplication. So that's x over x squared times x to the 12th. So this cancels one of those, that cancels one of those. So that's log to the base 2 of x to the 11. Or 11 log to the base 2 of x. I don't know. We could also just bring all the powers down from the beginning. That's another way. Log to the base 2 of x minus 2 log to the base 2 of x plus, bring the 3 down, multiply that, that's going to be 12 log to the base 2 of x. So that's like 1 apple minus 2 apples plus 12 apples is 11 apples. Get the answer to that. Now, one thing you should notice is that combining logs into one big log is very useful for solving equations. But expanding a log, taking a big log and breaking it up into smaller logs is very useful for calculus. So chances are, if you're in a calculus class, you're going to want to be expanding your logarithm. And in a pre-calc class, you're going to be wanting to expand your logarithm. So how you can do this is just realize that that square root really just means 1/2 power. You can bring that half down. And now this logarithm, I have a division which I can change into a subtraction. These parentheses, very common that someone would forget it. That's important, because this half has to be distributed across all the logarithms. Here's a multiplication. I can turn that into addition, but there's a negative sign that's going to be distributed. And the 3 I can bring down. So this 3 I can then bring down after the top. So this really expands to 1/2 ln of x squared plus 1 minus 1/2 of ln x minus 3/2 ln of x plus 1. And in calculus, there are certain things that if you want to do with this, it'll be a nightmare. But to do it with that, super easy. Do it in your sleep. So, we'll stop there. We'll solve equations and do more graphs next time. And I think start trigonometry for the next one.
我本来应该是加的，应该程序加嘛，但是前面有个括号。不是，你那个 L 里面的括号可能是相当于加号嘛，但是前面有个负，所以就变成那个什么，就变成减号。